What if I told you Elon Musk just shattered every theory about Starship landing without legs? While armchair engineers debated horizontal landings and legless concepts, Musk's own admission reveals the brutal reality. Those massive landing legs aren't optional. They're survival equipment. Here's what nobody saw coming. Despite catching rockets with Mechazilla, despite revolutionary engineering, Starship absolutely cannot touch down on the moon without legs. But it's not about weight or complexity. It's about 6 Raptor engines that become useless death traps the moment you try landing sideways. The physics are terrifying, and Musk finally explained why. Let's dive right in. The brutal truth behind Musk's statement traces back to a space race that's happening right under our noses. While most Americans celebrated SpaceX's incredible Mechazilla catches, former NASA Administrator Jim Bridenstine issued a stark warning. We could lose the moon to China. This isn't political theater. China has committed massive resources to reach the moon by 2030, systematically studying and copying SpaceX's innovations, while NASA wrestles with Artemis program delays and budget constraints. The question isn't just who gets there first. It's who stays and builds permanent operations. That's exactly why Starship's landing system matters so much. Every engineering decision, from engine placement to leg design, directly impacts humanity's future in space. Get it wrong, and you're not just risking a mission, you're potentially handing space dominance to another nation. So what made engineers think Starship could land without legs in the first place? The concept seemed brilliant at first glance. Instead of balancing Starship vertically on mechanical legs, why not land it horizontally like a giant spacecraft lying on its side? The concept seemed brilliant at first glance. Instead of balancing Starship vertically on mechanical legs, why not land it horizontally like a giant spacecraft lying on its side? The physics actually supported this idea. The moon's gravity is only 1/6 of Earth's, meaning Starship's 120-ton mass becomes just 20 tons on the lunar surface. The spacecraft's entire hull could distribute this weight evenly across the ground, eliminating the balance problems that come with standing 50 meters tall on landing legs. Even better, horizontal landing would solve the surface stability issue that's plagued lunar missions. The moon's regolith, essentially powdery soil mixed with rocks, makes vertical landings treacherous. Recent private missions like Intuitive Machines' Odysseus and Astrobotic's Peregrine both tipped over during touchdown, highlighting just how challenging lunar landings can be. SpaceX even included horizontal starships in their Moonbase Alpha concept art, showing how landed vehicles could integrate directly into permanent lunar facilities. The engineering community embraced the idea, with countless forum discussions and academic papers exploring the possibilities. But Musk's recent technical explanations reveal why this seemingly elegant solution contains a fatal flaw. Here's where Musk's admission becomes crucial to understanding the engineering reality. Starship's 6 Raptor engines aren't just propulsion systems. They're the spacecraft's primary guidance and control mechanism during landing. Every successful landing requires precise thrust vectoring, where engines gimbal tilt to make minute adjustments during descent. These engines must fire in perfect coordination to slow the spacecraft, maintain attitude control, and execute the final touchdown sequence. The system allows Starship to hover, move sideways, and place itself exactly where mission planners intended. When engineers proposed horizontal landing, they overlooked a fundamental physics problem. Rotating Starship 90 degrees also rotates those 6 engines from pointing downward to pointing sideways. Suddenly, your precision landing system becomes nearly useless. Even if we wanted to land on the side, Musk explained in technical discussions, the engines lose their main superpower, controlling the landing. Without downward thrust, the engines can't slow vertical descent or provide the delicate control needed for safe touchdown. This revelation transforms the entire landing equation. Instead of a controlled descent, horizontal landing becomes an essentially ballistic approach, more like a controlled crash than a precision landing. The implications for crew safety become immediately apparent when you consider what this means 240,000 miles from Earth, with no rescue mission possible. The natural engineering response might be to redesign Starship for horizontal landing, add side-facing thrusters, modify the hull structure, relocate critical systems. However, this approach reveals why SpaceX's best part is no part philosophy led them back to landing legs. Consider the cascade of changes required. You'd need entirely new thruster systems for horizontal descent control, additional fuel tankage to feed them, modified structural reinforcement to handle sideways loads, and completely different life support in crew egress systems. The crew compartment, designed for vertical operations, would require fundamental redesign. Even basic functions become complicated. Starship's crew door assumes astronauts will exit onto a stable platform when the vehicle stands upright. In horizontal configuration, crew members would essentially climb out of a sideways building onto loose lunar soil, creating both safety hazards and operational difficulties. By the time engineers finish these modifications, they wouldn't be building Starship anymore. They'd be creating an entirely different vehicle, one that's heavier, more complex, and paradoxically less reliable than the original design. This analysis brings us back to the core engineering principle that SpaceX discovered through Falcon 9's development. Sometimes the most complex-looking solution is actually the simplest one. SpaceX's confidence in vertical landing comes from years of successful Falcon 9 operations. Since 2015, Falcon 9 first stages have executed over 200 successful vertical landings using a proven four-leg deployment system. The Falcon 9 landing legs use lightweight carbon fiber and aluminum honeycomb construction. During ascent, they fold tightly against the rocket's body to minimize aerodynamic drag. Seconds before touchdown, gravity assist deployment, while pneumatic actuators powered by high-pressure helium lock the legs into position. The system demonstrates elegant engineering, simple deployment mechanisms, lightweight materials, and reliable operation in the harsh environment of rocket landings. Most importantly, it proves that vertical landing with deployable legs can be operationally reliable for dozens of flights. However, scaling this technology to Starship presents new challenges. Starship's 9-meter diameter and significantly greater mass require 6 legs instead of 4, each substantially larger and stronger than Falcon 9's hardware. The increased complexity serves a crucial purpose: redundancy. If one leg fails during lunar landing, the remaining 5 can still provide stable support. This redundancy philosophy mirrors Super Heavy's 33-engine design. When human lives depend on the system, backup options become essential. But lunar operations add complications that Earth-based Falcon 9 landings never face. Landing on Earth gives Falcon 9 predictable concrete pads or drone ship decks. The Moon offers no such luxury, only regolith, rocks, and craters that make every landing site unique and potentially treacherous. Lunar regolith behaves differently than terrestrial soil. Formed by billions of years of meteorite impacts, it consists of fine particles mixed with larger rocks, creating an unpredictable surface that can shift under load. This variability means one landing leg might sink deeper than others, potentially causing instability in Starship's towering 50-meter frame. Recent private lunar missions highlight these challenges. Intuitive Machines' Odysseus lander tipped over during touchdown in February 2024, while Japan's Slim lander ended up nose down after a leg failure. These were relatively small, lightweight spacecraft. Imagine the consequences if a 120-ton Starship carrying astronauts experienced similar problems. The stakes escalate dramatically when human crews are involved. Unlike cargo missions where some risk is acceptable, crewed landings demand near-perfect reliability. A tipped Starship doesn't just mean mission failure. It could trap astronauts or prevent their return to Earth. This reality drives SpaceX toward advanced landing leg designs that can adapt to uneven terrain and provide maximum stability under all conditions. While SpaceX solves engineering problems, Congress plays politics with billion-dollar budgets. In 2025, lawmakers passed what insiders call One Big Beautiful Bill that locks NASA into continuing SLS, Orion, and Gateway programs through 2029. The numbers are staggering: $1.025 billion annually for SLS, $750 million for Lunar Gateway, plus another $1.25 billion to keep the International Space Station operational. That's over $3 billion per year for systems that many experts argue are redundant with Starship's capabilities. But here's the kicker. NASA's own Inspector General called the agency's 50% cost reduction promises highly unrealistic. Even optimistic projections keep SLS launches above $2 billion each, while SpaceX aims for dramatically lower costs with full reusability. Remember Elon Musk's 2017 presentation, where he claimed Starship could handle entire moon missions without local propellant production? The concept was revolutionary. Launch from Earth, refuel in high elliptical orbit, fly to the moon, land, and return home, all with one vehicle. We can actually do lunar surface missions with no propellant production on the surface of the moon, Musk explained. That would enable the creation of Moonbase Alpha or some sort of lunar base. The architecture was elegant in its simplicity. No SLS, no Orion, no complex orbital rendezvous. Just Starship, orbital refueling, and those crucial landing legs making it all possible. Could this have worked? The physics say yes, but only with reliable landing systems. Those legs aren't just hardware, they're the foundation of the entire mission architecture. While America debates congressional funding and engineering trade-offs, China quietly advances toward their 2030 lunar landing goal. They're not just building rockets, they're copying successful concepts and potentially avoiding the mistakes that slow Western programs. Former NASA officials warn that China's focused approach and massive resource commitment could lead to a lunar presence before Artemis fully operational. The question isn't just who gets there first, but who stays and builds sustainable operations. This is where Starship's landing leg design becomes strategically critical. Reliable, reusable landing systems enable frequent missions, permanent bases, and genuine lunar colonization. Get the legs wrong, and you're stuck with one-shot missions that can't build lasting presence. Throughout all the technical debates and political maneuvering, one reality remains constant. Human lives hang in the balance. When Starship HLS carries astronauts to the lunar surface, every system must work perfectly. Landing legs might seem like mundane hardware compared to revolutionary engines or heat shields, but they're literally the first thing astronauts depend on when they reach their destination. No legs mean no stable platform. No stable platform means no safe exit. No safe exit means no mission. This is why Musk's admission about landing legs isn't really an admission at all. It's an acknowledgement of physical reality. Some engineering challenges have elegant solutions. Others just require building the right hardware and making it work reliably. None of this matters without solving orbital refueling. Starship can't reach the moon and return to Earth on a single fuel load. The mission requires multiple tanker flights, fuel transfers in Earth orbit, and precise coordination of complex operations. SpaceX has successfully demonstrated these concepts in test flights, but operational reality demands near-perfect execution. Every tanker flight, every fuel transfer, every orbital maneuver must work flawlessly to deliver astronauts safely to the lunar surface. The landing legs become the final link in this complex chain. After months of preparation, multiple launches, and precise orbital choreography, success ultimately depends on 6 mechanical assemblies deploying correctly and keeping a 50-meter spacecraft stable on alien soil. Modern Starship missions integrate multiple cutting-edge technologies: Raptor engines, heat shield tiles, life support systems, guidance computers, and yes, landing legs. Each component must work individually and as part of the larger system. The legs interface with the guidance system for deployment timing, the structural system for load distribution, and the propulsion system for landing coordination. A failure in any area cascades through the entire vehicle. This integration complexity explains why SpaceX chose evolution over revolution for landing systems. Falcon 9's proven leg technology provides a foundation that can be scaled and improved rather than completely reimagined. Beyond single missions, landing legs enable permanent lunar infrastructure. SpaceX's Moonbase Alpha concept shows horizontal starships integrated into surface facilities, but they still need to land vertically first. Reliable landing systems enable cargo deliveries, crew rotations, and equipment transport that make permanent bases possible. Without dependable legs, lunar operations remain limited to brief surface visits. Exactly the limitation that makes Chinese competition so concerning. The vision extends beyond national prestige to economic opportunity. Lunar resources, space manufacturing, and deep space logistics all depend on reliable surface operations that begin with successful landings. This bigger picture explains why getting landing legs right matters more than solving them elegantly. The moon doesn't care about engineering aesthetics. It only responds to systems that work under extreme conditions, with human lives at stake. What does this mean for the future of space exploration? The answer might surprise you, and it goes far beyond just landing safely on the moon. This is exactly why Musk's admission about landing legs matters. It reveals the fundamental difference between engineering for headlines and engineering for human survival. While critics debated elegant theoretical solutions, SpaceX quietly solved the harder problem: building systems reliable enough to bet human lives on 240,000 miles from home. Those simple landing legs represent America's true competitive advantage in space. Not flashy innovations, but proven systems that work when everything else fails. What this means is profound. China can copy SpaceX's rockets, but they can't copy a decade of operational experience that teaches which engineering compromises actually matter for human spaceflight. These mechanical legs unlock humanity's expansion beyond Earth. Reliable landing systems enable the cargo deliveries, crew rotations, and permanent bases that transform space from exploration to colonization. Within 5 years, Starship HLS will prove these systems work with human crews on the moon. By 2030, multiple starships operating simultaneously could establish the logistics network for permanent lunar infrastructure, giving America a multi-year head start over China's 2030 landing goal. The question isn't just who reaches the moon first, but who builds the foundation to stay permanently. Do you believe SpaceX's focus on proven, reliable systems gives America a lasting space advantage? Or will China's rapid development approach ultimately prove more effective? Your thoughts could shape how we view this new space race. If this analysis gave you new insights into why seemingly simple engineering decisions matter for humanity's future in space, hit that like button. Drop a comment with your prediction. Will America maintain space leadership through reliable engineering, or will speed beat safety in the long run? Subscribe to Space Hub and ring the notification bell. We're the channel that goes beyond viral space clips to explain the engineering decisions that actually determine who leads humanity to the stars. Because the next breakthrough in space exploration might not look like a breakthrough at all, until you understand why those 6 landing legs could be the most important hardware ever built for human space travel.